Hey guys, so in this video we'll talk more about what we started working on in the last video. First thing I want to do is another bit of terminology. I know we threw out a few important terms last time. We talked about normalization, that the probabilities have to add to 1, and that our state vector, the vector that represents the state of a particle, because probabilities have to add to 1, also always has to have a magnitude of 1. The other thing we talked about is a superposition, right, which is this combination of having some probability of being in one state or the other upon measurement. Again, the particle is in an inherent state of probability, an inherent superposition. It's not in one or the other, and then you just have to measure to find out. It's really truly in either. It's really like in any of them, and all of them kind of at once. In a way, it's in that superposition until you measure it. Okay, so now the other thing I want to throw out is the term Hilbert space, because that's what this whole mathematical setup is called. It's called a Hilbert space, where we have these axes and these vectors that represent some observable quantity. That's just in physics and math terms, that's called a Hilbert space. Okay, so now we've got another thing to consider when you talk about the Stern-Gerlach experiment, because I've been talking like there's just these two quantities. There's color and there's hardness, but it turns out that there actually are more quantities than that. And I've got a PhET simulation that I will show you, and I've got a link in the description that will talk about sort of how there's a bunch of other quantities sort of in between. You may call them intermediate quantities. So here we have a simulation from PhET on the Stern-Gerlach experiment. So the first thing we have here is this these two boxes. Essentially this one that's vertical is going to be our color box. This one will be our hardness box, and we've got, for example, here in the positive end, we'll say that's the white electrons. These are actually atoms in the simulation, and so but it's basically the same thing, whether or not it's electrons or atoms. Actually, I think usually the experiment is done with atoms and not electrons, but same kind of idea. And then here we have the soft electrons. So as you'll see, if we fire atoms, or we can just do an auto fire, just a bunch of them all at once, you see we have about 50-50. This is sort of random-ish, so there's always going to be a little bit of error in there. But this is exactly what we expect. If we add a third box, this will be our color box. As you see, we're taking all the white ones, then all the soft ones. You would think maybe all of these would be soft and white, but as we know, once you measure the hardness, you no longer know what the color is. So as you see, we still get that 50-50. But for example, if we measured the color again, we would get 100% getting through, right? Okay, so now the other thing is there are more quantities than this. So we have our color box and our hardness box, but maybe there's some quantity a little bit different. So like, for example, this quantity here is pretty close. If I just all of the two boxes, this quantity here seems like it's closer to being a color box, and indeed, the ones that come out of this, the positive end, which we can label that as the white end of the color box, are far more likely to come out of the positive end of this other box that is closer to being closer to being a color box than a hardness box. Similarly, we can get something much closer to being a hardness box that, as you can see, it's about 50-50, because this property is closer to hardness. Although if we add another hardness box to it, auto fire there, you can see almost everything that comes out of the positive end of this middle box ends up being soft, coming out of the positive end of the hardness box. So the point that I want to show you is that there are more quantities that are kind of intermediate between color and hardness. You could the one that we'll be dealing with is going to be what I'll call shape, which will be about like this, where it will be a lot closer to being color than it is to being hardness. But you can play around with this simulation, see that there are these quantities sort of in between color and hardness. Okay, so as you can see, there are some intermediate quantities in there that are not either color or hardness. They could be closer to being color or closer to being hardness. So I've got one that I'm going to talk about here, and let's call it. Hopefully, you've known that these are not real physics terms, color and hardness. It's just a way of sort of understanding the situation. And so let's make up another term. We're going to call it shape. Okay, so the shape. And we'll put them on green axes here and say we've got shape is going to actually look like it's a little closer to color than it is to hardness. So if we have this, okay, so the two shapes that it could possibly be are the electron could be round, or it could be flat. Okay, so I guess we're, it's either like round, like a sphere, or flat, like a piece of paper. Okay, so now this will be our round axis. This will be our flat axis, and then we can have unit vectors on them. Let's see so hopefully you can sort of tell what I'm doing here. You may have noticed I expanded the diagram a little bit because things were about to get kind of crowded. So we've got a round unit vector and a flat unit vector. Okay, and similarly, we can write the state psi is a superposition of being round and flat, just like we can write it as a superposition of being black and white or hard and soft. So psi can also be written as C round, that's the round unit vector, plus C soft, it's the S unit vector. Okay, and now, right, we've got really an infinite number of options we can have. We can sort of spin these axes a little bit. Now, one thing to notice here is you can kind of see graphically, if a particle is round, it's far more likely to be white than it is to be black. Similarly, if it's round, it's slightly more likely to be soft than it is to be hard. And you can sort of see that sort of by the relative components here, right, in sort of the soft direction. But so now, right, writing all of these unit vectors in terms of the other and trying to figure out, if I've got a particle that has some probability of being round and some probability of being flat, what are its probabilities of being hard and soft, right? This can get a little bit cumbersome if we just have, an arbitrary number of different bases that we could write this in. So there is actually a better way to figure this out, and it's using the dot product. And again, hopefully you're familiar with the dot product. You can look at my video on vectors, which I'll have in the description. And so what we can do is we can show that so say we want to isolate one of our properties here. So let's say we want to isolate CW. Okay, CW is the dot product of the white unit vector and psi. Okay, because if we write psi in terms of in the color basis, got white dotted on CW is the white unit vector, plus C black times the black unit vector. Okay, but now if we sort of expand this out, this is you can take the constant out of, or the scalar out of the dot product. So this is CW times white unit vector dotted on with the white unit vector plus CB times the white unit vector dotted on the black unit vector. But the white unit vector and black unit vector are perpendicular, which means their dot product is 0. And the white unit vector dot product with the white unit vector is, well, we know that any vector, I'll just say V dotted with V, is the magnitude squared of the vector. Right, that's a dot product identity. And so this is the magnitude squared of the white unit vector, but it's a unit vector, so its magnitude is 1. So we are left with CW. Great, and by the same logic, right, you can say isolate C, oh, I don't know why I wrote S here. Hopefully you caught that mistake. That's supposed to be an F. If I can erase that here. Okay, so, yeah, so anyways, if we want to isolate CF, we could just do the flat unit vector dot product with psi. And this should work in any basis, right? It doesn't matter what basis you express it in, the dot product will be the same. Hopefully that makes sense. The dot product is sort of just saying what is the component parallel to a certain vector, which sort of makes sense using it in this context. So geometrically, this should also make sense. And you can write psi in any basis, and if you do the dot product, you will get the coefficient back. So this is sort of our general way of extracting a coefficient from a state vector. Right, that's what we'll call it a state vector, and we can isolate the coefficient by taking the dot product. So I want to really write this down, and this is going to be our first main postulate of quantum mechanics. And I'm going to refer to this as our probability postulate. So let phi, this is going to be a state, the Greek letter phi, be the state with a definite value of some observable so it has a definite value of some observable, we'll call the observable capital Q. So it has a state with a definite value of some observable Q being little q. Okay, so the observable is Q. It has a definite value little q. So for example, if big Q could be, you know, the observable color, and little q could be being white or being black. And then, so if a particle, right, and again, if Q is white, then phi would be the white unit vector. If Q is black, phi would be the black unit vector. Same thing if it were hard or soft or round or flat. So if a particle is in the state psi, then the probability of measuring the part of upon measurement, so that's what the probability is. Once you measure the particle for the observable capital Q, the probability you'll get the value lowercase q is, it's going to be the phi dot product with psi squared, right? And what this means is IE, right, this is CQ. We can get that coefficient by taking the dot product. So like in the example we had before, I didn't fully finish it, but the probability, if I were to ask, what is the probability of the electron being white, it would be, right, CW squared, which is white unit vector dotted on psi squared. So anyways, we are back here. So this is what this is saying is CQ is, oh, not in that color, CQ is phi, right, the state with the definite value, dot product with psi. Okay, so that is our probability postulate. Now, the last thing that I want to talk about in this video is a special case of this. Where, so let's say, special case. Special case is psi equals phi. Right? And what that means is the particle is already in the state with the definite value of Q. Right? That's what psi is. Psi equals Q. Psi, the state of the particle, is in the state with the definite value of Q. The probability of getting Q then would be, well, phi dotted with phi squared, which is the magnitude of phi. This would be to the fourth power, right? Because this is the magnitude squared and then squared, right? But this has to equal 1, because if it's in the state, if the particle is in the state with a definite value of Q, the probability of getting that definite value that it has is 1, right? That should be logic, right? But if this magnitude to the fourth is 1, this means the magnitude squared would also be 1, right? Because the magnitude squared couldn't be negative 1, right? Or, which would also mean the magnitude would be 1. So this shows why it's so important that our basis vectors, so our, like, for example, our white unit vector, our black unit vector, those are our basis vectors, those have to be normalized, right? This is magnitude. Those have to be normalized in order for this probability postulate to make any sense. So that's why I wanted to highlight that special case. Okay, so I will see you in the next video, and we will put some more onto our idea of a Hilbert space, including complex numbers.